now let's continue with AI and machine learning concepts. So we spent time on understanding what data science is and the difference between data science, machine learning, and AI. And it's very important to understand that even before we get our hands dirty on nuts and bolts of how we can build these systems. So we'll spend some time on what is the meaning of machine learning and what is the meaning of AI and how do they differ. The idea is to see the basic building blocks of machine learning and get the basic vocabulary, and also look at some of the major machine learning algorithms that we will be using in this course. Just a diagram that machine learning, where machine learns from the data, the future that we would see. Look at some of the definition of machine learning. One of the famous person in this field, it's an informal definition for that matter. So it's the field of study that gives computers the ability to learn without being explicitly programmed. So that's the informal definition. For example, self-driving cars. So in the traditional way of programming, computer programming, so you would probably have the rule-based, condition-based programming, where all scenarios are envisioned at the beginning of your exercise, and you will be able to code. You should be coding for all those scenarios. If there are any new data or a missed scenario that come into your play, then pretty much your program will ignore that or give you an error. That's the traditional computer programming. But when it comes to machine learning, it's the ability that computers get to learn from the data without being explicitly programmed. So it can see the new data and it can really address that, whether it is a classification or a regression, with a probabilistic response. It's not deterministic, but it is probabilistic. So then let's look at the scientific definition of machine learning. It's from Tom Mitchell, who is one of the pioneer in this field, who's a professor or a dean in Carnegie Mellon University. So his definition is a computer program set to learn from experience E with respect to some class of task T and performance measure P. If the performance at task in T as measured by T, it improves with the experience E. So let's break it down. For example, like if you're conducting a dialogue, E is the experiences of many dialogues. So that's basically your training data set. So you have collected many dialogue, many data set for dialogue. And the task which are being collected is the task of talking like a human, right? Say the dialogue is like task of talking like a human. So the program that you are writing or the model that you are building gives you the probability that the program will convince you that it is a human. Let's say you collected some dialogues of human and dogs barking or some other animals making some other sounds. But the objective that you have is that given those data set, what is the probability or identifying any given data set that convinces that it is a human. So that's the relationship between the experience and the task and the performance of the model, right? So the objective here is to maximize the probability, which is the performance number that we are looking at. Given the experience and the model that you build, the probability outcome, which is measured as the performance, should be the maximum. So we tend to go with the maximum recommendation. For example, the same case, if the outcome of that probabilistic model that we built, it says it's 78% it's a human, and about 10% it is a dog, and about 12% it is something else. So in that case, our recommendation is, of course, it's 78%, which is highest probability. Then we go with that decision classification that the dialogue that is produced in this case is a human being. So that's the basic idea the scientific way of looking at the machine learning. And in machine learning, data science world, you will end up doing several linear algebra, and some of you may have gone through this, studied this in your grad or undergrad. In the case of machine learning, we will be leveraging the linear algebra matrices and calculations. For example, if you take house pricing prediction, where you have lots and lots of features that are coming in as an house feature, could be like number of bedrooms, square footage, zip code, and many other things. So each one of them are called features. So you basically have n number of features, and there are so many houses in your training data set. So you have m number of houses in your training data set. So basically you have the data, which is in the form of a matrix in n by m. So you have n number of features and m number of houses. So it becomes a linear algebra from there, where you have to work with many of the weights that you would be calculating, the biases that you would be calculating, whether it is a linear regression or a logistic regression. It applies to all the rows and columns, and that's where the linear algebra come into a play, and we will be doing some of those things in the classes that we have. So if you look at the history of AI in 60s, it's mostly we had commercial computers and mainframe. The only artificial intelligence that we had those days were computers play chess, and I'm sure that everybody's familiar with. Then in 80s, AI were pretty much in theory, and in fact they got oversold and didn't live up to the expectation, and it became mostly a hype. Then in 21st century, about I would say a decade and a half ago, the big data and the cloud changes this equation. So you have access to lots and lots of data, and you have the ability to consume them, process them, and store them with the big storage and big compute. And that's what really you see AI in action. So there are many big organizations like Microsoft and Google. They are pretty much investing on creating this AI cognitive services. There are some that links that I have there. You'll be able to go and see them in action and how these AI models are being used in the cognitive services. So in AI, so you have this classical machine learning, and you also learn about lots of deep learning and neural networks. So they were not able to be used in the real world with the neural network algorithm approach. And that's when, like, we didn't have lots of applications in the real world. But as we talked about, with the more and more compute, we get to see the neural network in action. The advantage of some of this neural network that we see, the accuracy is a lot more higher than the traditional approaches that we have seen. Again, it goes back to prove the point that the more data beats even the best and best of the algorithms that we have.